All right, guys, so today we're moving on to section 3.4. 3.4, there are going to be three big ideas. One of them is concavity. One of them is called a POI. Does anybody know what a POI is? Point of inflection. And then the third thing is something called the second derivative test. Now, hopefully you've already watched the video that I produced about a month ago and posted on Canvas. If you didn't, I highly encourage you to watch that video. In that video, I do different examples than this, but I'm doing it again live and in person so that you guys can see it live in person. So my objectives today, again, talking about concave up, concave down, points of inflection. That's what we call POI, point of inflection. And then the second derivative test. Now, guys, I would encourage you to not write much down. If you want this, just send me an email. I'll send you a copy of this presentation, okay? Open your brains and listen to me as I try to explain this stuff to you. First of all, let's talk about the definition of concavity. That's our first fancy word for the day, concavity. If f is differentiable, then we say a function is concave up if f prime is increasing. By the way, what is f prime? It's the slope of the. So look at my example right here. Would you agree that there's a tangent line drawn here, a tangent line drawn here, and a tangent line drawn there? What do you notice about these slopes? Here's slope 1, here's slope 2, here's slope 3. What would you say is happening between those three slopes as we move from left to right? Would you agree that the slope is? That's what the definition says. Similarly, it's called concave down if f prime is decreasing. Okay, so slope of tangent line here, slope of tangent line here, slope of the tangent line here. What's happening to the slope? It's decreasing. It's getting smaller and smaller, becoming more and more negative. Concave up. See how it's kind of caving upward? And then this is called concave down. Right? So how do you figure out where a function is concave up or concave down? I'm going to skip that example to save a little bit of time. This is the slide. This is probably the most important slide for concavity. This is the test for concavity. And remember, I said today's lesson, we're going to be focusing on the second derivative, and that's what we're going to do. Let f be a function who has a second derivative. If f double prime is greater than 0, guess what we're going to call that part of the function? Concave up, which is nice. That's kind of intuitive, right? F double prime is greater than 0, therefore it's concave up. Remember, concave up is like this. That's concave up. Second part. If f double prime is less than 0, then it's going to be concave down. So that's how you'll test. If I ask you determine where a function is concave up or concave down, you will look at the second derivative to do that. If the second derivative is positive, then it's going to be concave up on that interval. And if it's negative, it's going to be concave down. By the way, this is in my notes that are posted on Canvas, this theorem. Now, again, I'm going to encourage you, don't write this down. Just watch me. There's more stuff I'm going to put up here than you have a chance to write down. Just open your brains. So here's a function. Here's its derivative. I saved this step of doing the derivative. You'd have to do the quotient rule twice, or you'd have to do the chain rule twice to get this derivative. You would agree that finding that derivative would probably take you a little bit of time, wouldn't it? Now remember, since we're asking about concavity, that's why I'm interested in that second derivative. So now we're going to do something like we did in the last two sections, except this time we're going to look for critical numbers of the second derivative. Critical numbers of the second derivative. By the way, remember, a critical number is where the derivative is equal to 0 or d and e, correct? Is there any way that this denominator can be 0? Well, the answer is no. If you try to solve x squared plus 3 equals 0, you will find that there is no real number solutions for that. How could I make the numerator 0? 1 and negative 1. So our critical numbers of the second derivative are 1 and negative 1. So what I'm going to do is this. I'm going to do that little number line thing like we just did on the warm-up, and I'm going to put those two numbers on there. And now this isn't f prime. This is actually f double prime. Okay, now let's play the game again. Let's start with an easy one. What is a number between 0 or negative 1 and 1? 0, I kind of said it. 0, right? So if you plug 0 into this, first of all, the denominator is going to be positive, wouldn't you agree? 0 squared plus 3 cubed is going to be positive, agreed? Notice that I don't really care what the answer is. I just want to know if it's positive or negative. Now let's do the same thing on the top. 36 is clearly positive, correct? If I plug 0 in there, it's clearly positive. But what if I put 0 there? What do I get? So I got a positive times a negative times a positive, which makes the numerator negative. Are you with me? So that's negative. That's when I put x equals 0 in there. And by the way, what's negative divided by positive? Well, that's negative, correct? That means this is negative, which means I'm telling you the curve is going to be concave down there. We'll see that in just a second. It's concave down. What's a number bigger than 1? 2. What if we plug, now first of all, if I plug 2 in the bottom, it's still going to be positive, correct? If I plug 2 in there, what do I get? If I plug 2 right there, what do I get? Everything I just said was positive, so what's the answer there? It's positive. So guess what the concavity is going to be there? Not positive concavity, it's be concave up is the word we use. It's concave up. Now, by the way, you'll notice when I did the warm-up, we did the exact same thing, except I would have put f prime, correct? And then I would have put a little arrow going up or a little arrow going down. Remember that? Notice here, instead of doing the little arrows, I'm doing the little concave symbols. And by the way, I'm just going to cheat here a little bit. I'm going to tell you if you plug in a number less than negative 1, it also turns out to be positive. So when we put all of this together, you get some sort of chart like this. If you want to do a more detailed chart, you can, or you can just do like I did. It turns out that it's going to be concave up here, which is negative infinity to negative 1. It's going to be concave down here, negative 1 to 1. And it's going to be concave up there as well. In fact, here's the graph of the function. Guess what we call the concavity here? Concave down. Guess what the concavity is here, even though it's very slight looking? It's concave up there. And guess what the concavity is there? So this is an example where the function is concave up, concave down, and then concave up again. Okay? Now, I want to point out something before we do our next example here real quick. You might want to take a guess at what we call those points right there. And by the way, it's not a min or a max, is it?
Critical numbers.
They're critical numbers of the second derivative, but if I want to take a guess, I said there was 3 things we needed to know today. One was concavity, one was second derivative test. You remember the third thing? Point of inflection. These are called points of inflection. I'm kind of getting ahead of myself a little bit, but point of inflection is where the concavity changes. So notice here it was concave up, and then here it's concave down. So guess what we call that point right there? A point of inflection. Okay. Very similar strategy as we've been doing for section 3.3 with increasing and decreasing. It's just now we're dealing with the second derivative. Okay. So let's look at another example. I'm going to just breeze right through this one. This one's a quotient one, right? We have to do the quotient rule. Here's the derivative. Again, that would take a while for us to do. We could play the game again. By the way, is there anything we could put in the numerator to make that 0 or make that 0? Nope, because you cannot solve this for real numbers. What would make this 0? 2, right? What would make this 0? Guess what the critical numbers are over the second derivative here? 2 and negative 2. So I'm going to just show you, I'm going to kind of cheat here a little bit because we just did one exactly like this, almost just slightly different. This is going to turn out to be, and this, by the way, is F double prime. This turns out to be, I think this one's negative, so it's concave down. This one's positive, so it's concave up. Am I doing that right? I'm going to cheat here a little bit, guys. I can't remember what the graph of this one. I did it backwards. All right. Actually, let's just leave it there. We'll fix it. I think it's almost exactly like the last. I think the last one was the same thing, wasn't it? So this is going to be concave up, so it's positive. This is concave down, so it's down. Now, why I did this example in addition, guess what we call this point right here, which, by the way, isn't even there. We don't call it anything. It is not a point of inflection. Guess why it's not a point of inflection? Because it doesn't even exist. Guess what we call this thing? It's called an asymptote. Now, I'm making this point on purpose because I'm just telling you that in the future, you're going to be asked about concavity or points of inflection, and students will get through all this stuff, and they'll say, okay, that's positive, that's negative, that's positive, and then guess what they'll say about x equals -2? They'll say it's a point of inflection because they'll say it went from positive to negative, but there's a problem here. There's not a point there in the first place. And we'll see that in just a second. I just want to show you an example. And by the way, would you agree that this example is very similar to, sorry, let me get back to the last one. The last one. Concave up, concave down, concave up, correct? Now the numbers here are a little bit different. Oops. Same, exactly. Graphs are way different though, aren't they? Way different.
How can you tell if it's going to be asymptote or point?
Just like right there.
If it's D and E, then it has to be an asymptote.
You know right away that this is going to have two vertical asymptotes at 2 and -2. So that's a good indication. Okay. Remember that from algebra 2? I mean, that's algebra 2. Okay. All right. So we have just talked about concavity, right? Concave down, concave up. Now let's talk about points of inflection. And I just kind of already started talking about them a little bit to kind of front load some stuff. Now, please be aware, this theorem it's an if-then form. You guys remember if-then form type questions? If P, then Q? This one is saying if it's a POI, then the second derivative at that value has to be 0 or it has to be D and E. It doesn't tell you where they are. It just says if it's a point of inflection, then it had to occur at these critical numbers of the second derivative. And it turns out that those critical numbers of the second derivative have to be either 0 or D and E. This is very similar definition to our critical numbers from earlier in this chapter. Now, let's talk about points of inflection. This right here, it turns out that F double prime is equal to 0 at this point right here. And notice it's concave up to concave down. So guess what we call that? Point of inflection. Here's another example where F double prime is equal to 0. Anybody want to take a stab on what F double prime is in this last picture though? D and E. What's the slope of a vertical line? D and E. So that's why we have to include this D and E part. Okay? So let's look at an example of finding actual point of inflection. Now this problem, I'm actually going to work this one out from the get-go. And the reason I'm going to do this one is because it's going to work out very nicely because it's a nice polynomial function. By the way, what time do we normally need to stop here to make sure we get time for announcements?
We don't have to do announcements.
46, so 36. Okay, we're good. 36-ish. Okay. All right, let's go ahead and do some derivatives here. What's F prime?
4x to the third power minus 12x.
Are you guys getting good at this, the derivatives using the power rule? That's easy, right?
Yes.
Okay, now we're going to go to the second derivative because we're trying to find points of inflection. Second derivative is going to be 12x squared minus. Now, this is the second derivative, but guess what I would encourage you to always do when you're doing these without a calculator and by hand? Factor them. Can this be factored? Well, of course, right? Would you agree that both terms have a 12 in them and both terms have an x in them? So this could be rewritten as 12x times x minus 2. And we want to set this equal to 0 or D and E, right? Now, we don't need to do D and E in this example because that's super easy. The domain is all real numbers. When is that going to be 0? 0 and 2.
A 0.
So a 0. So our critical numbers of the second derivative are x equals 0 and positive 2. Does that make sense? Now again, we're doing points of inflection and concavity right now, not max and mins. So we're going to do that same game that we did just a second ago. Guess what two numbers I'm going to write on this graph? You guys, 0 should come before 2, right? A 0. You should be kind of catching there's some redundancy in some of the stuff we're doing, right? Remember, this is f double prime. What's a number less than 0? Okay, if I plug -1 into there, which is less than 0, if I plug -1 into there, this is negative and this is negative, correct?
Yeah.
Which would make it
Positive.
positive. Is everyone clear? This is positive, so it's going to be concave up. Okay, what's a number between 0 and 2? Positive 1 would be an easy one to pick. If I put 1 in there and 1 in there, I'm going to get a positive times a, which makes it negative. So I'm telling you, now listen guys, I'm telling you, every number between 0 and 2, when you plug it into the second derivative, is going to be negative. Every one of them. It doesn't just mean 1 is, any of those numbers. You guys want to take a guess on what the answer is going to be out here for 2? It turns out that it is positive. So, what do you think this is? It's going to be a point of inflection. Guess what this is going to be? Another point of inflection. Let's see what the graph looks like. We have a point of inflection right here at 0. That's a POI, points of inflection. Right here at 0, 0 is a point of inflection. The reason it is a point of inflection, let me do this in green, is because here it's concave up and here it's concave down. Does that make sense? Okay, similarly, down here we had another point of inflection. Because what was it right here? It was concave down, correct? What is it over here? Concave up. So guess what we call this point here at 2? I think it's -16. That's going to be a point of inflection. So there are 2 points of inflection. Oh, I should mention this. You guys understood where I got the 0 and the 2, right? Do you guys understand where the -16 comes from? How would you find the -16? Well, you plug the 2 into the original function. By the way, this is the graph of f right here. This is f. This is not f prime and this is not f double prime. Okay? Does that kind of make sense so far? We've talked about concavity on all 3 examples. And now in this example, we talked specifically about points of inflection. There's 2 of them. Comments or questions on concavity or points of inflection? By the way, so far, both things involve the derivative, the second derivative, right? Oh, I guess let me mention one more thing before I do the last topic. Most always it goes, like just with increasing and decreasing, most of the time it goes positive, or negative, positive. It normally alternates. But guess what they almost always do on the AP exam? They'll give you one where it doesn't. They'll give you one where it'll go positive, negative. So I'm just forewarning you. And all you got to do is check. I'm trying to kind of go quickly through this so that we got time to hit all the topics. Okay? All right, let's go ahead and get to the last thing, which is the second derivative test. This is the third and final exclamation point. We've done concavity and we have done points of inflection. Finally, we need to do something called the second derivative test. Now, before I even tell you what the second derivative test is, let me emphasize this. Just like, do you guys remember we just talked about on the warm-up, the first derivative test? We use the first derivative test to do what? Find relative extrema. Agreed? That's what we use the first derivative test. Guess what we use for the second? Guess what we do with the second derivative test? The same thing. Now, the reason I'm mentioning that is sometimes students, I'll ask a student, like, where's the function concave up? And they'll say it's concave up from 3 to 5 or whatever. And then I'll say why. And guess what they'll say? The second derivative test. Does the second derivative test tell us anything about the concave? Do we use that to find concavity? No. We use it to find relative extrema, okay? We're going to use concavity to do that, but that's not the purpose of the test. And the reason I'm saying that is I want you to sound like you know what you're talking about when you say I'm using the second derivative test. Do we use the second derivative to find concavity? Yes. Do we use the second derivative test to find concavity? No. We use the second derivative test to find extrema. Now, guys, this is super easy if you think about it, okay? But it's not intuitive. You see this curve right here? What is this, a relative min or a relative max? That's a relative min, isn't it? It's a valley, right? But what's the concavity there? Concave up. Think about it. Think about, in your mind, try to think of the lowest point on a curve. What's the concavity going to be there? It's going to be concave up. Similarly, but differently, what do we call this guy right here? That's a relative max. What's the concavity there? Down. That's the facts that this theorem uses. If we get a critical number, by the way, I should note this. This is a critical number of the first derivative because the critical numbers of the first derivative is where we have possible extrema. If we plug that into the second derivative and it turns out the second derivative is greater than 0, in other words, it's concave up, then it's a relative min. That's this example here. If we plug that critical number into the second derivative and it turns out that it's less than 0, then that means it's concave down, which means it's a relative max. Unfortunately, we have one piece of bad news. If you plug the critical number into the second derivative and you get 0, guess what? This test fails. You cannot use it. You then have to go back and use the first derivative test. Okay? So I'm going to try to get one more example in here before we need to stop, and we're getting pretty close. Again, I picked a nice, easy one, right? So let's just go ahead and do this here, if that's okay with you guys. And by the way, the first thing you got to do is find the critical numbers, right? Because we're trying to find, what are we trying to find? Extrema, relative extrema, right? So what's f prime? Well, that's easy. That's negative 15x squared plus 15. Oops, that should be to the fourth. Sorry, x squared. Can I factor that?
Yeah.
Okay, so let's factor that. Would you agree they both have a negative 15x squared in them? Okay, so that would be what, x squared minus, is that 1? Can x squared minus 1 be factored?
Yeah, 1 minus 1.
X plus 1, x minus 1. Good. So f prime of x is equal to negative 15x squared, x plus 1, x minus 1. So therefore, what are our critical numbers? Negative 1, 1,
0.
and don't forget this guy right here. A 0. My favorite number to say. Okay, so we found our critical numbers of the first derivative, and guess what we're going to do with those? We're going to plug them into the second derivative. So we're going to find the second derivative. Let's go ahead and use this now to find the second derivative, this guy right here. So what's the derivative of that? Negative 60x to the third. That's 60, not 66, sorry. What's the second derivative, or the next derivative of that? 30x. Can that be factored?
Yes.
What do they have in common?
30.
Do you mind if I say negative 30x? I'm gonna say negative 30x. So then what times negative 30x gives you negative 60x cubed? X squared, and then a 2 in the front of that, right?
Yeah.
And then what times negative 30x gives you positive 30x? Minus 1. Can this guy be factored? The answer is yes, but it would involve irrational numbers. I'm going to do it anyways. Maybe I'll just leave that for you to think about. Okay? Anyways, so here's what we're going to do now. We're going to take this stuff and we're going to plug it in to that. Okay? So let me do that in green. What is f double prime of, let's start with the easy one, 0. Actually, no, let's not do that one first. That seems like an easy one, but I want to save that one for last. Am I green? Yeah, cool. Let's do negative 1. If I plug negative 1 in here, I'll get the following. I'm going to get negative 30 times negative 1 times 2 times negative 1 squared minus 1, right? Okay, what's negative and negative? So far, that's positive. So that's positive. And what about this here? Negative 1 squared is times 2 minus 1. Positive, right? So this is positive. Agreed? Which means it's concave up. Therefore, x equals negative 1 is the location of a relative what? Concave up. Relative min. You with me?
Yeah.
Now I'm going to go ahead and show you the picture here. What did we say it was? Relative min. When you plug 1 in, guess what you end up getting? Because f double prime turns out to be less than 0. You with me? Bad news. Guess what happens when you plug 0 in? Look what it says. Ooh, right here. Guess what happens when you plug x equals 0 in? You get f double prime equals 0. What does that tell us? The test fails. By the way, is 0, 0 a relative min or a relative max? Neither. It went from increasing to increasing. So it is neither a min or a max. Got it? Now, guys, I've covered a ton of stuff today. We talked about concavity, concave up and concave down. We talked about points of inflection, where the concavity changes. And the third and final thing we talked about is the second derivative test. I'm going to go back to this one. It has been my experience from teaching this class. I'm going to get rid of as much of this as I can. Students have a hard time remembering this one. And one of the reasons is they say, Mr. Allen, why can't I just use the first derivative test? And the answer is, you can. Why would I ever use a second derivative test? Because sometimes it's really easy to find the second derivative. And sometimes on the AP exam, on multiple choice questions, they'll give you the second derivative. And they'll say, determine what the relative extrema are. So you need to know this. I remember last time we met last week, I said the most important test was the first derivative test. I said that was the most important test. This one is not as important, but I will test you on it. You need to know it. I'm going to stop there, which is perfect.